range sum of BST. So what is the problem? Given the root node of a binary search tree, return the sum of value of all nodes with value between L and R inclusive. So we have given a BST. The binary search tree is guaranteed to have unique values. So all the values are unique in the binary search tree. So if you take this binary search tree and L value is 7 and R value is 15, so output should be 32, which can be seen as here. If you see, this is our binary search tree, same binary we are talking about in this example. So this binary search tree having root 10, then 5 and 15 are left and right child of 10. So root is 10, 5 and 15 are left and right child, then 3, 7, null and 18. 10, 5, 15, 3, 7, null and 18. So this is the representation of binary search tree, and since L value is 7 and R value is 15, so we want summation of all those values which are greater than L, that is 7, and less than 15, that is R. So these three values that I circled are the one that we need to add in our solution. So if you observe, this is a binary search tree, which means it is having the binary search property. So what is binary search property? So binary search property is nothing but if you take any node of the tree, the left subtree of that particular node will have all the values less than the value of root. So root is 10 and all the nodes in this left subtree are having value less than 10. All the nodes in the this subtree are having value greater than 10. Okay, so how we'll go about solving this problem? We can easily solve this problem using recursion. So what we need to do, if we will always start our traversing the tree from the root node, and we will write a recursive function where we will check if our root node is lying between 7 and 15 both inclusive, then we need to add the 10 value in our answer, and then we will go in the left subtree and do the same thing, and also then we will go in the right subtree and do the same thing. So if you reach at the 5 node, since 5 value is not within the 7 and 15, we will not consider this value, and we may optimize the solution. If 5 is already less than 7, we don't need to call any of this branch. Okay, so we can reduce these functions calls where our if the value at particular node is less than L, then we don't need to go at the left subtree of that node. Similarly, if our value is 18, then we don't need to go at the tree which is at the right of 18, right subtree of 18. So since here there is no right subtree at 18, we can skip that part for now. So we will see two solutions. First solution, without pruning these things, which will be our Tropan solution. But if we want to optimize, we can optimize it also. So let's see the first solution. How we'll write the code. So this is the Python, and we have the class tree node, which is defined as we have three things, value, left and right. These are the variables which you can see. And now we need to complete this range some BST function. So how we can go about it? So I will write first the recursive part. So if our root value, if root dot val in range L comma R plus 1. Okay, so this is the easy way of writing in Python. If our root value belongs in this range between L and R, then in our answer, so I will take one variable return value equal to 0 initially. So if our current root value belongs between the range of L and R plus 1, then we should consider the root value in our return value. So what I will do, I will add the root dot val in the return value. So this is the about the root. So since now we are doing it without any pruning, so we'll call for the left subtree and for the right subtree. So this function I will call for left and right both. Okay, so here self dot range some BST. If you know the Python, this is mandatory to write self and root dot left L R and so this is a function called for left subtree. Okay, so I will add whatever answer comes from the left subtree, that should also be added in the return value. So initially return value is 0, then we added the root value, then we add the answer of left subtree, then we will also add the answer of right subtree. So I'll copy this answer of right subtree, root dot right. So now I can return this value, return. So but we need to do the base condition also. So what will be the base condition? If root equal to none, then return 0. This is our base condition. Let's check whether it will work. It's working fine in this case. Let me submit. It is accepted. So this was a solution without any pruning. It is going to consider the whole subtree, but we can make these calls conditional. Okay, these called conditional. So when we can make these called conditional, so this left subtree should only be called if our root value is greater than L, greater than or equal to L. Oh, since they have distinct value, so we can say greater than is sufficient. So I will prune it. So if root value is greater than L, then we should call this. And when we should call the right subtree, so if our root value is less than R, then only we should go in the right subtree. So if our root value is less than R, then we should call this function. So it will slightly optimize the running time. Uh, Asymptotically it will be same, but it should reduce some time. Let's see whether it works. Yes, it is working. Yes, it is working. It is working fine. If you observe here, it was taking 344 millisecond without pruning, but now it is taking 232 millisecond. So it is slightly better solution. So this is Ankit Bhardwaj signing off.